Are we recording? Yeah. All right. So fires and explosions, part 1. We know that fires and explosion is the most common types of accident in the oil and gas industries. We've seen a lot of them. In the first 3 weeks of our lecture, we've seen a lot of examples. So now we will focus more on the behaviors of fires and explosion, how it happened, why it happened. Okay, the nature of fires and explosion is will be more detailed. Last Saturday there was a webinar organized by SPE on ICEX on becoming a competent person on something regarding to explosion. Did anyone get to join that webinar? No?
No, doctor. No.
So it was an interesting webinar because they talk about fires and explosions and the industry, not just oil and gas industry, but in all types of industries. Okay, so the learning objectives of this topic is, first of all, we will describe the nature of fires and explosions. So to describe this, we will use the fire triangle. So you will define, I'll introduce you to the fire triangle and then define the elements in the fire triangle and explain also how to use it and how to prevent flammable mixtures. And then third objective is to characterize the flammability of gases, liquids and dust. Fourth objective is to estimate the flammability parameters for mixtures. So not just for a single element, also for mixtures. And then also we'll see how to draw a flammability triangle diagram and then also apply it. Number 6 is to identify types of fires. So we see there are many different types of fires. So we see the different types of fires. Well, a good way to do this is to watch a lot of videos. So we'll be seeing a lot of videos. And then number 7 is to describe the effects of fire on people. And finally, you will learn how to estimate the effects of fires on people using the Probit equation. So it's an equation where you can determine the impact of the fire to properties, to people, whether you're going to die from it, whether you're going to get minor injuries or major injuries and so on. Okay, so the content of this topic is mostly from the book Chemical Process Safety, Fundamentals with Applications. And this book is available, you can find it online or at the library. So if you need more information on this topic, you can read more from the book. Okay, so we've seen these 3 most common chemical plant accidents: fires, explosions, and toxic release. Toxic release is like the one in Bhopal or Chernobyl. Okay, so we will be focusing on fires and explosions in this topic. Okay. And we have also seen the impacts that it can bring to many different, to people, to properties, to the environment, as well as to the business itself. So it impacts all of this. Okay, so I want to start with one example. This is an example where we can also relate to the domino theory, which we have learned in the theories of accident causation. So the story about Mumbai High North is that this oil platform, the whole thing was gone in 2 hours. So this 2 hours explosion and fire has destroyed the whole platform. So it's really quick. So the main reason, or how it all started, is because one of a cook, it started from a cook in the kitchen on the vessel, not even on the platform. So on a ship, which is a multi-purpose support vessel, on the ship there are kitchens. So the cook cut his fingers, 2 of his fingers, and he needed medical attention. So to get medical attention, he needs to be back on the platform somehow. He has to go back there, and he had to be transferred to the platform from the vessel by basket transfer. And then somehow that ship hits the risers and then causes gas leakage and then finally just explodes. and the whole platform was lost. So you can see that's the domino theory, where it starts with the unsafe act by the cook that cut his own fingers, and then maybe the negligence of the ship to hit the risers, and it's just exploded. And then there might be other reasons too. Okay. So this just shows you in just 2 hours it can destroy the whole platform. So this is why it is important for engineers to know or equipped with the knowledge about fires and explosion. Because to prevent the accidents that result from these kinds of fires and explosion, you must know the properties of materials. We handle flammable materials such as methane, ethane, butane, all the hydrocarbons, all the alcohols, and the other petrochemicals. Those are all flammable. So you need to know what is the property of the material. What is the flash point, for example? What is the ignition point and vapor pressure? So those things are important. And then you need to know also the nature of the fire explosion process. How does a fire start? So you need to know what makes up a fire. And then it is also important to know how to reduce hazards that's related to fire and explosion. So you need to know how to handle or control fire-related accidents by following the procedures to reduce hazards. Okay, so let's talk about the fire triangle. Now the fire triangle explains that there are 3 elements that must be present in order for fire to occur. So first of all, for you to have fire, you need to have fuel, right? So without fuel, how can you have fire? So you need to have some kind of fuel. It's either a liquid fuel, solid fuel, or gases. So liquid fuel are like all those hydrocarbons or alcohols, or acetones. Okay. And then there's also solid fuels. Solid fuels can be anything that's flammable. It can be even the table, what we call a wooden table. It can be plastic. Some plastics are flammable. It can even be dust, wood dust, milk powder, even flour. Those are all combustibles. Okay? Fibers, cloth, metal particles, even those are all flammable. And then gases, yes, gases is always flammable. Acetylene, propane, hydrogen. And then if you only have fuel by itself, safely contained in a container, you won't have any fire. I mean, you cannot ignite any kind of fire from it. So you need to have an oxidizers, because we know that in order for you to make fire, you need to have gas such as oxygen. So you blow when you're starting a campfire, right? You need to have enough oxygen for it to start burning. So other gases are also oxidizers such as fluorine and chlorine, and some oxidizers can be liquids like hydrogen peroxide, nitric acid, perchloric acid, and even solids such as metal peroxides and ammonium nitrite. And just fuels and oxidizers alone is not enough. You need to have an ignition source. You have a fuel, you have an oxidizer. So how to start a fire? So you can start it with a flame, for example. You have a small flame, and then you can start the big fire. Sparks can also start fires, as well as static electricity. For example, if you're wearing a flammable clothing, and if you rub your clothing another surface and creates charge and creates a static electricity, so that can jump to the fuel and oxidizers and start a fire. Okay. So not just sparks, flames, and static electricity, heat also can start a fire. If you have really high heat, say the condition is just so hot, you have very high heat, that can also start a fire, as long as the heat has enough energy to start this fire. So now we know that we have all these 4 elements, right? So in order for you to extinguish a fire, you just have to remove one of the elements. Okay? So you won't have any fire if, for example, you remove the fuel. So you don't have any fuel present, or the fuel is just not in sufficient quantities. You have very little fuel, then you won't have fire. Or you can remove the oxidizer. Or it's just that the oxygen is not sufficient enough. This is like when you have a fire, when something's on fire, you put a blanket on it. That's a way of removing the oxygen from that source of fire so that it can be put out or extinguished. And an ignition source is not energetic enough to initiate the fires, then you won't have any fire if, say, the heat is just not high enough, or the spark is just too small, and so on. Okay, so these 3 elements work together. Without one of it, you won't start fire. Okay, so that's fire. Now, what about combustion? Okay. So combustion, or even fire, okay? So combustion really is a chemical reaction in which you have a substance, which is your fuel, and then you combine it with an oxidant, and then you have heat released. So this is when you have heat release in a chemical reaction, that means it's an exothermic oxidation, and a typical combustion equation would be a fuel or a hydrocarbon plus oxygen. In a perfect combustion with enough oxygen, normally you would have CO2, right? And water, if you still remember your combustion equation. So that's what you get. So it's a chemical reaction. Another thing that's important for you to understand is combustion always occurs in the vapor phase. It's always in the vapor phase. If not, it won't occur. Okay, so this is because when you heat something up, let's say you heat up a flammable liquid, so that liquid will volatilize, so it becomes a vapor. It is now in a vapor phase. Or if you burn a solid fuel, for example, so that solid fuel decomposes and it also turns into vapor. So you see, it's always in a vapor phase. So when that concentration of that vapor phase is high enough, that vapor becomes a flammable mixture and then mixed with enough oxidant with the oxygen in the air. Okay. So if this flammable mixture, it already has 2 components. It has the fuel in the vapor phase in the right concentration. It has oxygen is also in that vapor phase in the right amount of oxygen. You just have to add an ignition point. You just put a spark, for example, the combustion will start. So that's how you start a fire. So you need to have that 3 elements. One is the fuel in the vapor phase, and then it's mixed with enough oxygen with the oxygen. Together it becomes a flammable mixture, and then just add an ignition point, you start the fire. Alright, so this is what we always see how a fire looks like, right? Typically for most hydrocarbons, if you see this kind of fire, you see smoke, right? Do you see black smoke? This is normal, right? For fires, you see black smoke. And what's the color of the fire? These uncontrolled fires, they're always orange and yellow, right? Right?
Yes.
Okay. So this is typical. You can see it from far. Yes, you see this orange yellow flame or reddish flame with black smoke, or sometimes grayish or white smoke, depending on what's the type of hydrocarbon. Okay, so you have it's visible to your eyes. However, there are some kinds of fire that you don't see the fire and the smoke. So there are smokeless fires. For example, in the case of carbon disulfide, this is where you don't see the flame and you don't see any smoke. So this is a fire, an intense fire going on right now. If you can see this, let me make a pointer here. If you see this area here, you see this yellowish kind of like gas coming out like a wisp of sulfur. Okay, so this is the combustion process going on. Okay. This combustion is just as intense, it's just as robust as the previous hydrocarbon combustion. It's just that it's not visible to the eyes. You don't see the fire, you don't see any smoke. Okay? But the amount of heat that's being released from the exothermic reaction is just as high as the typical hydrocarbon combustion. Okay. All right, another type of combustion behavior is this example. Let's say you have a methane that is burning within a vessel. You have a closed vessel and the methane is, this one is in a dust filter unit. Okay? So it's in a covered vessel burning the dust, and due to pressure buildup, it starts to shoot out of the building. They look for the weak spots in the structure and have this projection of fire going out of that containment unit or tank. Okay? So this is one behavior of combustion where you have this like jet-like propulsion of fire going out of source. And another behavior of combustion, this is also again, you can have a combustion in air with dust. Yeah? This is in the air. It's just like the one in the previous slide where you have a combustion going on in this vessel. I think this looks like a cyclone. It looks like a cyclone where it, if you remember what cyclone does, cyclone actually removes the particles, dust particles. So it's probably the combustion probably started inside the cyclone, and then due to the lack of oxygen, but the fire is still intense, but it's trying to look for oxygen. So it escaped this vessel and tries to look for the oxygen that's outside of that vessel. So it's now burning outside because there's more air. Okay? So, but much of the dust are burning in the chamber. It's just that the reaction continued, or the explosion or fire continued outside of this vessel just because it can find enough air. And so this is the behavior of fire, because fires, they move. Okay, so I've been talking about fires and explosions. What's really the difference between fires and explosions? We always say that fire is a friend, right? We need fire. We need it to cook. We need it for heat. As long as we can control that fire, so it's beneficial to us. If the fire becomes uncontrollable, then you can have an explosion. So you see the difference is how you control something. What is it? You control the reaction. You control the amount of heat that's released. So you see, the major distinction is the rate of the energy release. For fires, it can take a while for you to have fire to start. But combustion can start in seconds, even microseconds. Okay. So fire releases energy slowly, whereas explosion releases energy rapidly in order of microseconds. It's just like that, you can have a fire. And then fires can also result from explosions, and explosion can result from fire. So there, see, it's like if you can control it, it can go back to fire, or it is uncontrollable, it explodes. So now let's look at some definitions that is related to this topic. So first of all, so we've gone through this combustion. Combustion is a chemical reaction in which you have a substance, which is a fuel that combines with an oxidant, which is the easiest one will be oxygen, and then it releases energy in the exothermic reaction, and part of the energy is used to sustain that reaction. Ignition is caused by a flammable mixture coming in contact with a source of ignition with sufficient energy. Like I said just now, you have a flammable mixture. You have, like, you know, this thing that you use to start a fire, that the spark gun thing, so that you can start a spark and ignite the fire if it has enough energy. Auto ignition is another interesting definition. Auto ignition temperature is the temperature above which adequate energy is available in the environment to provide an ignition source. This is when you don't need any, you don't need that spark gun to start a fire. If you have a flammable mixture, and for example, that flammable mixture is concentrated enough, and the environment is also hot enough, it has so much energy in the air, it can start a fire. This is normally, it's basically like what happened in forest fires. Sometimes forest fires, it just starts, it can start on its own due to auto ignition. Okay, so two more definitions that's important: flash point and fire point. So we always hear this. Flash point is the temperature above which a liquid, so you have a liquid, it produces enough vapor to form an ignitable mixture with air. So the liquid is producing that vapor that's enough for it to become flammable, okay? And with it mixing with air. And this is only for liquids at 1 atmospheric pressure. So after the flash point, just a little bit above of the flash point temperature, you have the fire point. The fire point is the lowest temperature at which that this vapor is now above the liquid will continue to burn once it's ignited. So it's usually higher than that flash point. So first you have a flash point where you have the liquid, it volatilizes, producing this vapor, and that vapor is concentrated enough and mixed with air, then it reaches a flash point. A flash point where it can start to have a first flash, but that flash will not continue burning. It's just a flash. But once you heat it up a little bit more, then that flash will continue to burn. So that is the fire point. Okay. Are you confused between flash point and fire point, auto ignition?
No, doctor.
Okay, everybody okay?
Good.
Okay,
All right. Anyways, just to strengthen your understanding, this is a good video to watch. It's that's oh my gosh, where? Okay, okay, my pointer cannot click on this. All right, there it is. Okay, let's go to this YouTube video and see. I hope I put the audio on.
Every few minutes, just pop that and see what temperature the gas is, or the fuel is. Canola oil inside.
184.
What we've got, canola oil in a pot, and just to demonstrate, got a lighter. I can put this in here. I can put the flame surface directly on the oil. It's not going to catch on fire. Reason being, it's just not hot enough. We're not giving off the amounts of flammable vapors that are required to heat that up. I can go straight down to the bottom surface of the grease, and we've still got nothing. All right, I'm starting to see some smoke coming off the top. Now, what we're talking about, concept being that smoke is the smoke will burn, but not yet. Start seeing the kind of a smoky stuff coming off. Now that's what we're talking about when we're talking about the vaporization, where we talk it's pyrolysis when dealing with the solid. called vaporization with the liquid. At this point, we're not quite there yet, but we're getting a lot closer.
560.
See, the fire won't start. And then flame. Yeah, it's not hot enough. Yes, hot.
And then it's the Thanksgiving fire.
All right, you hear that? Watch it. Oops. That's our flash point. That's our flash point. Now watch, I'll get it to
630. Y'all see it?
Yes.
Now look, we've got active flames. So we already went from our flash point to our flame point. This is our flame point, but if I put it out, cover it up, it stays out. We keep on heating this up though. That's our flame point. What do we want to keep doing at this point? That's our auto ignition temperature. At this point, we can cut the supply off, but it's hot enough, even without a direct flame,
Sweet.
where it'll catch on fire all by itself, and it's turbulent, it's moving around, it's trying to get going. And the idea is,
That's pretty sweet.
it's going to take a long time to cool off. So give it just from a far distance. Everybody step back now. Let's put it out from where you're at. Not at my camera.
No, that's why I go to
All right, don't splatter it out. Thank you. Hey, Jason, you got it too hot. All right.
No, up the station now. Can't search for him. That's true.
So that is, everybody get the difference now between,
I'm getting it.
Just like every time we learn something pretty hot.
really hot.
We're gonna have to. Somebody always wants a break, and I want to scream here.
All right. So that was the video that explains the difference between the flash point, the fire point, and the auto ignition. So was that a good video to watch?
Yes, Doctor.
Yes.
Yes, it was.
Okay, so you can see that the fuel that they used in this example wasn't really a hydrocarbon. It was just an ordinary canola oil, or it's just a cooking oil. So this is why it can be dangerous if you, let's say you accidentally heat up an oil just to fry something and you forgot to turn it off. It can catch fire because of the vapor that's produced above that oil. If it's high enough, it can get to auto ignition. Okay, so that's how fire starts in people's kitchen, for example. All right, next. Okay, so more terms. The limiting oxygen concentration is the oxygen concentration below which combustion is not possible with any fuel mixture. Okay, so the amount of oxygen is also important. You need to have enough oxygen for the combustion to become possible. So the limiting oxygen concentration is when the oxygen concentration is below the point when combustion will not occur. So that's the LOC. And the LOC is the primary design criteria to prevent flammable vapors. Okay, so remember this. This is an important term, limiting oxygen concentration, LOC. Sometimes they also call by different names. Some books call it minimum oxygen concentration. Some people call it maximum safe oxygen concentration, and there are also there could be many other variations. So it just means that that's a minimum concentration of oxygen that a combustion will not occur. Okay, so more terms. We have LFL and UFL. LFL is the lower flammability limit, and below LFL, the mixture will not burn because it is too lean, and then there's upper flammability limit. Above the UFL, the mixture will not burn because it is too rich. Okay, sorry about that because my daughter's here, but ignore her. Okay, so we'll look more on this LFL and UFL. Okay, we'll see what it is. I'll explain it later in the next slide. Because this slide is a bit boring. And there's also okay. So the LFL and UFL is defined by the gas percent of volume percent of that fuel in air. It can also be defined flammable limits in pure oxygen. In pure oxygen, they call it LOL or UOL, or sometimes they call it something else. Or sometimes they call it LFL, but with a O at a small O at the end, or UFL with a small O at the end, and LFL small O at the end. Sometimes they call it LOL or UL, but the LOL nowadays just means laugh out loud, so it's kind of weird to use that now. Okay, next slide. Okay. All right, so let me now explain UFL and LFL. Okay, let's say we take ethanol as an example. So ethanol has a lower flammability limit of 3.3% by volume, meaning that if the ethanol has a ratio of the ethanol vapor with air less than 3.3%, that vapor will not ignite, meaning the vapor is too lean, too little ethanol vapor in the air. So if you start a fire, it won't start because it's just too lean. You don't have enough ethanol vapor in the air. So 3.3% is the limit. Okay, at 3.3% it will ignite, but less than that it will not ignite. Okay, so if you increase the concentration of the vapor further, it will be flammable up to 19%. So 19% is the upper flammable limit UFL for ethanol. If you increase the percentage of ethanol, percent volume ethanol in air to 20%, for example, 30% or 40%, you won't have any fire occurring also. This is because the vapor, the ethanol vapor is just too rich. It has too many of the vapor, but not enough oxygen, so therefore it won't ignite. So different materials or different compounds will have its own UFL and LFL. So for the case of ethanol, the LFL is 3.3%, and the upper flammable limit UFL is 19% for ethanol. And these values are readily available in literature for all different types of compounds. Okay, for example, here this is one that I got from a book. So you have all of these different gases and vapors, and it has all these volumes too. We're looking at the LFL and UFL, so they're described in volume percent. We look down to, we were looking at ethanol, right? Okay, so ethanol here, you can see that the ethanol LFL is 3.3, and for UFL, let me use pen. You see, the LFL for ethanol is 3.3, and the UFL for ethanol is 19%, just like we've seen in the previous example. All right, so now let's talk about flammability relationships. Flammability relationships can be described in a vapor pressure or vapor concentration versus a temperature graph. Let me see. Okay, as you increase the temperature for a certain compound, for example, let's just if we stick to the let's just say methane. Okay, we have methane. As you increase the temperature of that methane, the physical condition of that methane will change from liquid to gas, right? Because it becomes more volatile as you heat it up. And the point where it changes into from liquid to gas changes depending on the concentration of that component. So that change, or that point where it transformed from liquid into gas is called the saturation vapor pressure curve. Okay, so this is the curve is an exponential curve, and from here you can see the relationship. There will be a point in this graph. Let's say this is a flash point, and just a little bit above it will be a fire point. It's not really shown here, and you can also determine where is the LFL and the UFL. Okay. So again, between the UFL and LFL is when the vapor will be flammable. So liquid is not flammable. Okay, remember it's always the vapor phase. This is the gas phase. So it's this area here is where the flammability zone is, and there's also the auto ignition area. So this is when it will ignite automatically without any ignition sources. And also you will realize if you see this UFL line, it's really not it's like an ascending line. Is going up. The LFL is also a little bit going down a little bit, but not as the slope is not as big as the one for UFL. And then here you can see that as temperature increases, so as you increase the temperature, you can see that this UFL also increases, and the LFL decreases. It becomes lower. So that means that this the flammability range also increase, right? And change, right? So this area here becomes bigger, right? As the temperature increases. If we look at pressure, if the pressure increases, okay, as the pressure increases, you also see that the UFL increases, but not much in the LFL. Okay. So this is the basic concept of a what we call of flammability. It's a relationship between temperature and concentration. Okay, so all of these flammability limits, the UFL, the LFL, okay, for all of these vapors like we see just now for ethanol, they're actually determined experimentally. So they did it in a lab, and then they just publish it and put it in tables and data tables in books. Okay. But if you have a mixture, let's say if you have a mixture of ethanol plus methane plus hexane, then the LFL and UFL now changes because it's a mixture. And you can compute the LFL and UFL of that mixture using Le Chatelier's equation. So the Le Chatelier's equation to compute the LFL of that mixture is 1 over the summation of the mole fraction of component I mean So it's the mole fraction of component I on a combustible basis. So let's say you have one component like the methane. So what is the mole fraction of methane? Divide by the LFL of that component. So divide by the LFL of methane. And then also you sum it with the second component. Let's say you have ethanol. So what's the mole fraction of the ethanol? Divide by the LFL of the methanol. And so on. You sum all of that component, and this N is the number of combustible species in that mixture. Same thing as the UFL for that mixture. Instead of LFL down here, it becomes UFL. And that is how you calculate the UFL and LFL of a mixture. For example, okay, let's say that you have a gas mixture that's composed of hexane, and it's 0.8% hexane, and then you have 2% methane, and you have 0.5% ethylene by volume. So with these things together, what is the LFL and UFL? So you can determine this by using these two equations. So let's see how to do it. Okay. And then also once we do this, we can also see whether this mixture is flammable or not. Okay. All right, so let's do this. So again, okay, question. You can it's good for you to have your paper and pencil with you. So and calculator, so we can do this calculation together. So what are the LFL and UFL of a gas mixture that's composed of 0.8% hexane, 2% methane, and 0.5% ethylene by volume? Okay. Okay, so you create this kind of table. Okay, you have this table, and you list out all of the combustible materials down here, and you write down. Okay, first of all, we have hexane. Hexane is 0.8 volume percent. We have methane, 2% methane. Ethylene is 0.5%. So you sum up all of this percent volume of this combustible material. 0.8 plus 2 plus 0.5 is 3.3 volume percent. So there's 3.3 volume percent of combustible material in this mixture. So the rest of it is air, and this is 6.7% air. Now remember the equation, you need to have that Y divided by the LFL or UFL. So the Y is the mole fraction of the combustible on combustible basis. So let's do this calculation. So the mole fraction of hexane, which is the first component, would be why is not writing? Okay, 0.8 divided by what?
1.2.
3.3.
3.3.
Total. Okay. So then you get the fraction. So 0.8 divided by 3.3. Tekan calculator, you should get 3.24. Betul tak? And then for the second component is methane. Okay, so this is 2 divided by 3.3. Ethylene 0.5 divided by 3.3 is 0.15. So that's the mole fraction. All right, so for the LFL and the UFL, so these two, you can get it from literature, okay? From data table, like the one I showed you just now. I have one in Padlet. You can also refer there. So I put in all the values from that data table. Hexane LFL is 1.2, UFL is 7.5%. Methane is 5% LFL, 15% UFL. Ethylene is 2.7% LFL and 36 volume percent UFL. So now you just calculate the mole fraction divided by LFL. So here will be mole fraction here is 0.24 divided by
1.2.
For the UFL would be 0.24 divided by
7.5.
7.5. Good. and so on. So let's do this and find the values. So this would be 0.65 divided by 0.65 divided by 2. Number 3 is 0.15 divided by 2.7. 0.15 divided by 36. Okay, so let's find all the values. And then once you have all of that value, you sum it up because you want to find the summation. Okay, now can somebody tell me what's the value here and what's the value here?
Zero 0.378.
0.37.
0.378. Okay, 0.38 lah here. And the next one is for UFL.
Zero 0.077.
0.07. Okay, good job. All right, so if you go back to that equation, remember the equation is for UFL and UFL and the LFL. Okay, so you have, it's the reciprocal, right? It's the reciprocal. It's 1 over that volume. So therefore, the LFL is 1 over 0.38. Okay, and the is 1 over 0.077. What do you get?
2.645.
2.64. All right, good. And the UFL is
13.
0.98.
13%.
13%.
13%. Okay, so that means this is the LFL of this mixture and this is the UFL of this mixture. Okay, so how do we know? And then the next question is, so we found out what is the LFL and UFL. So now it asks, is the mixture flammable? So how do we know if this mixture is flammable or not?
Below or above. LFL kena bawah, UFL kena atas.
So is this flammable or not? This mixture here. 0.8% hexane, 2% methane, and 0.5% ethylene.
No. Total combustible.
Okay, so we look at this now. The percent combustible material is 33%, 3.3%. So 3.3% lies between 2.6 and 30%. So that means is
Combustible. Makes flammable.
Yeah. Right. So that's how we determine the LFL and UFL of a mixture, and also to determine whether that mixture is combustible or not. Okay. Any questions? Any questions?
No, doctor.
Okay. All right.
Doctor.
Yes.
If the value is not between the UFL and LFL?
Then it's not combustible. If let's say if this total volume here is 2% or 1%, that means that the amount of vapor is just too low for it to start combustion. It's not
Okay.
enough. You need
Thank
to
you,
have
Doctor.
you need to have at least 2.64. That's the minimum amount of vapor that has to be present in order for it to become combustible. It's the amount of total combustible volume. On the other hand, if this total combustible is very high, let's say you have, you have 90% combustible material. Is all of it is just almost all of it is vaporized fuel. But then your air here is just 10%. Then it would not also become combustible, because it's because you have too much of the fuel, is too rich, and you don't have enough air. Then it won't be flammable.
Okay, understood.
Faham betul.
Okay, awesome. Okay, so next, okay, so again, we have seen just now the concept that remember that the graph just now between the what do you call the vapor pressure or the concentration, oopsie, and the temperature, right? Remember, and then we had that we had this graph just now where this is a liquid and then this becomes gas, and then you have this upper flammability limit, and then you have a lower flammability limit. Remember that one? And this one kind of like becomes like that. Okay, so it says that as temperature increases, so if this increases, you see that this one becomes it also increases. So the UFL also increases. So that's why all the value of the LFL and UFL that we've seen just now are all at 25 degrees C. At different temperature, that value changes. So if it's higher than 25 degrees C, you will have a higher UFL. And for LFL, okay, the LFL decrease, yeah, the LFL also becomes lower. So that means that you see that this region here actually becomes bigger as temperature increases. Okay, so this is the concept that you have to understand, that as temperature increases, the UFL will increase and the LFL will decrease also, even though that's just not so much, but a little bit, but it's still decrease. And therefore, the flammability range increases. So that zone of flammability increases. So at different temperature, you can also find the LFL or UFL using this equation. This is equation 6.4 and equation 6.5 in the book. And the temperature is expressed in degrees Celsius. And so to find this value in different temperature, you just need to have the temperature in degrees Celsius. You need to have the value of the LFL and UFL at 25 degrees C. And you also need to have this. You need to have the heat of combustion in kilocalorie per mole. And then you can find that specific LFL and the UFL at that temperature. Okay? All right. More flammability limit behavior. So now let's look at the pressure dependence. So as pressure increases, UFL also increases. So just now, I think it was like this, right? You have the pressure and the temperature. So as this is the upper flammability limit. So as temperature increases, the UFL also increases, but the LFL is not really affected. It doesn't have a lot of change. But again, you have this increased range of flammability region. To find UFL in different pressure is also possible. You can do this using equation 6.6, where pressure is measured in megapascal, and it is an absolute pressure. However, there are no theoretical basis for this yet. So pressure and temperature effects on flammability limits are still poorly understood, and these estimations, this equation for pressure and for temperature, the previous equations are really just a mere estimation, so you can't really rely on it because the estimations are quite poor. Okay, now more on estimating flammability limit. This is another way to estimate the LFL and UFL if you do not have the table of data or you do not have any experimental data. You can do this using an equation. For most hydrocarbon vapors, the LFL and UFL are a function of the stoichiometric concentration of that fuel. So normally, this is like a typical value. The LFL is about 55% of the stoichiometric concentration of that fuel. So it's 0.55 times CST, while the UFL is 3.5 times CST, and the CST is the volume percent in fuel plus air. So you can use these equations to find LFL and UFL if you do not have the data table or the experimental data. Okay, stoichiometric concentration for most organic compounds is determined using the general combustion reaction. We know that in a general combustion reaction, we have a fuel. Let's say the fuel is CHNO, and the coefficient here is M, X, and Y. So just remember, M is for carbon, X is for H, and Y is for oxygen. And then plus Z moles of oxygen, you get M moles of carbon dioxide. This is when you have complete combustion. And you have X over 2 moles of water. If you do the oxygen balance, so you will get that you get Y over 2, okay, plus Z equals to M plus X over 4. So if you rearrange, because you want to know what is the moles of oxygen needed for this combustion to happen, then you can have Z equals to M plus X over 4 minus Y over 2. So this is the equation that you use again. And then the stoichiometric and unit changes are required to determine CST as a function of Z. And so because we need that CST just now. So CST is the moles of fuel divided by moles of fuel plus moles of air times 100. So if you rearrange that, you get this 100 divided by 1 plus 1 over 0.21 because that's 21 is 21% oxygen times moles of oxygen divided by moles of fuel. And moles of oxygen divided by moles of fuel, let's see if you remember, Z is the moles of oxygen divided by moles of fuel. So you substitute with this Z here. So this whole thing is C. So therefore, you have this equation of the stoichiometric concentration, CST equals to 100 divided by 1 plus Z over 0.21. So this is the equations. And then next, when we have that, we can put back this into equation 6.7 and 6.8. If you remember this equation before, 6.7, 6.8, wait, this one. This one, LFL is 0.55 times the stoichiometric concentration. UFL is 3.5 times the stoichiometric concentration. Okay. So there. And this is the stoichiometric concentration just now, CST. So whole thing is CST. So whole thing is CST. Right? And then you put in there 4.76 M plus 1.19 X. And then you see here this Y, I can cancel it out because hydrocarbon mostly do not have any oxygen. And you can get it. Yeah. Yeah, right. So the CST is basically this one here, again. This one here, right? But then, mana datang all these things, MX mana? So that's actually Z is from here. Z equals to M plus X over 4 minus Y over 2. M plus X over 4 minus Y over 2. So normally for hydrocarbon, this becomes 0 because you don't have any oxygen. So that's why you have those values. So let's look at an example. Let's estimate the LFL and UFL for hexane. And then we compare these calculated values with the values that's available experimentally in data tables and so on. Okay. So hexane now. So we're going to look for the LFL and UFL for hexane. Okay, so first of all, we write down the stoichiometry of hexane combustion. Hexane is C6H14. C6H14 plus Z amount of oxygen will give you M moles of carbon dioxide plus X over 2 moles of water. So from here, remember the CmHXOY, right? So the M here is 6, the X is 14, and Y is 0. Okay, so M is 6, X is 14, Y is 0. Okay. So now let's calculate the LFL and UFL using equation 610 and 611. 610 and 611 is mana? This one, this equation here. So we use this and this equations. Just put in the values. You can try. Okay, let's calculate. M is 6, X is 14. So it's M is 6, X is 14, Y is 0. Put it in these two equations and then tell me what's the value of LFL and UFL. Okay, take out your papers. Let's calculate this.
Doktor. Untuk value MX dengan Y ni dia akan bagi
No. Well, it depends. It depends on the complexity of the molecule because this is hexane. Hexane, you should know what is hexane.
C6H14.
Kan? So C6 mana? C6H14. There's no O, right? The O is 0. Tak ada. Unless it gives you some, I don't know, substance that's, I don't know, like dimethyl, ethyl, chloropentane, then yeah, probably they will give you the molecular formula, and then you can find out what is the M and what is the X and Y. Okay, what's the answer?
19.59.
19.59.
LFL 1.19.
1.19.
1.19. Okay.
1.19.
UFL 7.57.
Okay. So that's the answer. If we compare from the data table, okay, if I compare with the data table for hexane, the value for LFL is actually 1.1 and UFL is 7.5. So it's a pretty good estimation, right? So we can use this. Actually, I've checked with a lot of these data table, because this data table is based on experiment, and experiment varies. Some books say that the LFL, I know some books tell me that the LFL is 1.2, another one say that is 1.1, another one also say 1.2, so there are some variation. Okay, for the UFL, I found one data says that the UFL is 6.9. Another table says it's 7.5, which is pretty good. And then there's another one says it's 7.4. Also not so bad. Okay, so you can see it's kind of varies because it depends on the I don't know, parameters in the experimentation. But anyways, so this is how you look for LFL and UFL if you do not have these data table, because they are pretty accurate. All right, would you like to take a break for a while, or are you good?
Take a break.
Okay, break.
Let's take a break.
Break. I need to drink some.